Today we're going to talk about Euler's method for systems. First, let's review some ideas from before about analytic methods for solving very special cases of systems of differential equations. Let's review a couple of main definitions. First, reviewed the idea of a two-dimensional system of first-order equations. This is the system of equations of the form d capital Y dt equals capital F of t comma capital Y, where capital Y is the two-dimensional vector x comma y, and capital F is also a two-dimensional vector in terms of lowercase f and lowercase g, two functions of three variables at t, x, and y. We'll say that the system is partially decoupled if either f is not a function of y or g is not a function of x. We'll say that the system is completely decoupled if both are true. We also define the idea of a second-order differential equation. This is an equation of the form d squared y dt squared equals g of t, y, and dy dt, where g is a function of three variables, t, y, and v. We say that we have an initial value problem if we have the extra two conditions, y of t0 equals y0, and y prime of t0 equals v0. We'll say that this equation is a linear equation if our function g is in the form g of t minus q of t times y minus p of t times v. That is, we have a differential equation of the form d squared y dt squared plus p of t times dy dt plus q of t times y equals g of t. We say that a linear equation is homogeneous if the right-hand side, g of t, is identically equal to 0. Otherwise, we say that this equation is non-homogeneous. We realize that if we're given a second-order differential equation, we can always express this as a two-dimensional system of first-order equations. This means that two-dimensional systems are more general than second-order differential equations. But there are some times when a two-dimensional system can be expressed in terms of a second-order differential equation. Let's consider that two-dimensional system in terms of constants a, b, c, and d that is in the form dx dt equals a times x plus b times y, and dy dt equals c times x plus d times y. We have two properties. First, say that capital Y1 and capital Y2 are two different solutions to this two-dimensional system. Then the linear combination capital Y equals K1 times capital Y1 plus K2 times capital Y2 is also a solution for any constants K1 and K2. Let's say that x of t and y of t are solutions to this system of equations. Then we also have solutions to a second order equation. That is d squared y dt squared plus p times dy dt plus q times y equals 0, where p is that constant equal to negative a plus d, and q is that constant equal to ad minus bc. Today, we'd like to discuss the idea of Euler's method for systems of differential equations. To do so, let's consider a motivating idea. A lot of this is based on the Dutch physicist named Balthasar von van der Pol. In 1929, he was interested in how to model heartbeats using a differential equation. Indeed, we know that the electrocardiogram, that is EKG, is a graph of voltage versus time of the electrical activity of the heart. So our motivating question is, can we model this voltage using a system of differential equations? Well, before we get into discussing voltage, we first need to discuss some properties of electric circuits. Here's an example of a circuit board. You probably have been very confused by all of these various components. We'll try to discuss a few of these today. But first, let's discuss some basic definitions that we'll need to focus on. Let Q of t denote the charge in the circuit at time t. Typically, this is measured in coulombs. We'll think of Q as the displacement y of t, in the sense of the spring mass systems we've discussed over the past few lessons. Let I, that is dq dt, denote the current. This is typically measured in amperes. We'll think of the I as the velocity v which is just y prime of t. We will be interested in the equivalent of electromotive force, also known as voltage. You want to think of this as mass times acceleration. The whole idea now is that we wish to discuss the specific formulas for voltage across four different objects. First, let's discuss the concept of an inductor. This is a component which stores energy in a magnetic field when the current flows through it. An inductor, simply put, is just an insulated wire wound into a coil. You can see some examples here on your screen. Michael Faraday was an English physicist who was very interested in studying the voltage across such devices. He showed that the voltage across an inductor is proportional to the change in the current in the circuit. That is, voltage of the inductor is L times di dt for some positive constant L. L here is typically called the inductance. It is measured in henries. We're going to see later that the inductor acts much like the mass in a spring mass system. The second I like to discuss is called the resistor. A resistor is a component which is used to reduce electric current flow. Ohm showed that the voltage across the resistor is proportional to the current. That is, V equals IR for some positive constant R. We typically call R the resistance, and it is measured in ohms. We'll see later that a resistor acts like a damping force in a spring mass system. The third I'd like to discuss is a capacitor. A capacitor is a component which stores electric energy in an electric field when electric current flows through it. Gauss's law has various applications, and one of them states that the voltage across a capacitor is proportional to the charge. That is, V equals 1 over C times Q for some positive constant C. We call C the capacitance, and it is measured in farads. We'll see later that a capacitor acts much like a spring in a spring mass system. And finally, I'd like to focus on what we'll call an electromotor force. This is a component that acts very much like a battery. The voltage in a battery might be a function of time. Of course, what that means is that the voltage in a battery might die as a function of time, or we might have something like AC, alternating current. In this case, the voltage is a sinusoidal wave. We'll see later that an electromotive force acts much like a forcing term in a spring mass system. Putting all four of these together, we have what's typically called an RLC circuit, R for resistance, L for inductance, and C for capacitance. This is just a minor bit of bookkeeping. We typically have chosen our units such that 1 volt equals a Henry ampere per second, or you can write this as an ampere times an ohm, or you can write this as inverse farads times coulombs. Kirchhoff's second law of circuits is much like F equals ma. It says that the voltage in a circuit must be the sum of the voltage drops across each of the items in the closed circuit. This means if you take a look at the diagram to the right of your screen, we have voltage V coming from a battery. This voltage must be distributed over the other three items here in the circuit, over the resistor R, over the capacitor denoted by L, and over the capacitor denoted by C. If we use the various formulas on the previous screens, and also recall that the current must be the derivative of the charge with respect to time, then we find a second order differential equation that relates charge as a function of time. Well, this is, simply put, the harmonic oscillator. Here, we will identify the inductance L with the mass m of a spring mass system, the resistance R with the damping coefficient B of a spring mass system, and 1 over C, essentially the capacitance, with the spring constant K. Finally, the electromotive force, which appears on the right-hand side of this expression, will be identified with a forcing term F of t. Now that we've discussed electric circuits, let's return back to van der Poel's ideas. As we just stated, let's say that we have the charge Q on a capacitor that's given some initial amount and some initial current. Then we have the following initial value problem. L d squared Q dt squared plus R dq dt plus 1 over C times Q equals E of t, where initially our charge at t0 is Q0 and our current at T0, Q prime at T0, equals I0. Van der Pol made the following assumption. In order to model the heart beating, he assumed that there is some type of a non-linear resistor. That is, first, we can make the same assumption as before, that the voltage across a resistor is proportional to its current. But second, he made a new assumption. Let's say that there is some threshold n such that the voltage across the resistor looks like Q squared over n squared minus 1 times our current I. Here's what this n represents. If our charge Q is greater than this threshold n, then that means that this component must draw a current away from the circuit. This is like the idea of a heart needing a charge in order to compress and push blood through. However, if Q is less than this threshold n, then a component feeds current back into the circuit. This is the idea of like the heart releasing, and it no longer needs the charge in order to hold together, to hold the blood pressure. Putting all of this back into our original expressions, we now see that we have the following modified differential equation. L d squared q dt squared plus r times q squared over n squared minus 1 times the q dt plus 1 over c times q equals E of t. This here is Van der Pol's equation. We will place this in a simpler form. The idea now is that we really don't care about the various units of this expression. So let's write q as n times a new function x, our current I as n times omega times a new function y, and E as n over c times a new function g. Here, omega is what's called the natural frequency of the system, and mu is some parameter that depends on the resistance R, the inductance L, and the capacitance C. Van der Pol realized in his 1929 paper that you can actually express this second order differential equation in a very simple form. We can actually express this as well in terms of a two-dimensional system of first order equations. This is what's known as the forced Van der Pol oscillator, although Van der Pol himself preferred to call this the relaxation harmonic oscillator. Please notice that if mu equals 0, then in this case, this is the same as saying that there is no resistance, and we actually find just the harmonic oscillator. That is d squared x dt squared plus x essentially equals 0. So this here is a generalization of the harmonic oscillator. We'll come back and discuss this a little bit more in just a moment. Intuitively here, x of t represents the charge, y of t represents the current, and g of t represents an external force, such as, let's say, a pacemaker. Now that we have this system of differential equations, let's discuss some numerical solutions. First, here we'll present an algorithm of how to numerically solve any two-dimensional system of first-order equations. First, fix a step size h, which we'll also express as delta t. We want to define two sequences of points as follows. Step number 1, let's compute a new time t sub k plus 1 in terms of the old time t sub k plus our step size h. Second, let's compute x sub k plus 1 in terms of the old value x sub k plus m sub k times h, where m sub k equals f of t sub k, x sub k, y sub k. Third, we'll do something similar for y sub k plus 1. We'll express this as y sub k plus n sub k times h, where n sub k equals g of t sub k, x sub k, and y sub k. And finally, we'll replace k with k plus 1 and do everything all over again by returning back to step number 1. All of this is known as Euler's method for systems. We've actually seen this before when we're just dealing with one first-order differential equation. As a remark, we may also wish to plot the points x sub k, y sub k to get another idea of how the solution behaves. Here's some specific numbers. Let's assume for the moment that g of t is identically equal to 0. That is, there is no external extramotive force. We'd like to get some data for the Van der Pol oscillator here when mu equals 1. You can see the table of data here on your screen. We've actually chosen our step size, delta sub t, to be 0.25, but you can still see the numbers that we find. course, if we decrease the step size quite a bit, then we can actually write down some very interesting plots. Here are some examples. First, let's take a look at the case when mu is equal to 0. Remember that this just corresponds to the harmonic oscillator. Well, we can see from the slow field on the right that we indeed do have the harmonic oscillator. Our solution simply spins around in this circular pattern. We can also see our solutions x sub t and y of t on the left. Essentially, these will just look like sines and cosines. Now, what if we increase this parameter mu just by a little bit? Now we can see what happens with the slope field on the right-hand side. We may start at an initial point, which is the brown dot, but eventually the black path moves around, and we see that we return back to some type of periodic pattern. This is actually what's called a limit cycle. It just simply says that everything really will spiral around in this pattern that will repeat and be periodic. You can also see some of the solutions on the left in terms of x of t and y of t. What if we increase mu even more? Now here's a plot when mu is equal to 3. On the right-hand side, again, you can see the slope field, and again, you can see this concept of a limit cycle. Here, it doesn't matter where our brown dot begins, we see that everything seems to tend towards this periodic, strange-looking pattern on the right. On the left, you can see the plot now of x of t and y of t. Indeed, these look very close to what we actually find in an EKG, an electrocardiogram. But of course, this is exactly the reason that Van der Pol considered his oscillator in the first place. Thanks very much for watching.